So right now we're taking a look at problem number 41, and it's modeled after example 4 on page 225. I want to save you some time and energy here. I want you to take a close look at the graph of the bell curve or the Gaussian model on page 225 and notice the X and Y scales. Since we're talking about SAT scores, the X values, the only ones that make sense, are between 200 and 800. But what didn't make sense to me at first, and the reason I saw a flat line when I graphed this over and over again, is because the Y-axis, the window, is from negative 0.001 to 0.004. So keep that in mind as we go through problem 41 and you're graphing this. 41 says the IQ scores for adults roughly follow the normal distribution. Anytime we see normal distribution as a model, we know that we have a Gaussian model, and we need to pay close attention to those X and Y values. The normal distribution is 0.0266 times e to the negative expression x minus 100 squared, all divided by 450. For Pete's sake. The X values that make sense, the way that we've set up the domain, is between 70 and 115, where X is the IQ score. X is the IQ score. Use a graphing utility to graph the function, and use the graph in Part A to estimate the average IQ, keeping in mind that the average in a bell curve is exactly in the middle. Until you take further statistics courses, you'll understand quartiles and such. When we're looking for the average of something in a Gaussian model, we're looking for that maximum value, and in this case the IQ score being the X value. So let's go ahead, stop here, get your graphing calculators out, put this in, pay close attention to your Y values, but of course set your domain for 70 to 115. So back to problem 41. We've got our function in our function editor, and we're looking at the picture graph. I want to make sure, I'm going to reiterate, that when you're doing these Gaussian models, I want you to look at the window. I did a zoom fit. Whoa, look at all those. So zoom fit, option 10. And what that did for me was pull the window in that would best fit all of the data. You can see it maxing out at the top of the window. If you look at the window, from 50 to 150 definitely covers our domain that they wanted us to have, 70 to 115. But if you look at the Y min, 1 to the negative 4, this is 0.0001, and the Y max, 0.0266, and going up by a scale of 1,000th. These have extremely tiny increments on the Y axis, and you need to keep that in mind. I graphed a lot of flat lines last night trying to figure this out until I looked at one of the samples they had. So we need to keep that in mind for the range. If we look back at this graph, the first question says, use the graphing utility to graph it, complete the model, solving for K, back up, use the graphing utility to graph the function, and then use the graph in Part A to estimate the average, keeping in mind the average hits right in the middle. So we could use our trace function, where at x equals 100, for some reason it jumped right to it, you can see it right up there, x equals 100 would be our average IQ for the adults in this problem with this distribution. So that's how we're going to use our graphing utility, keeping in mind raising to this power, you need everything in parentheses if it's being squared, and making sure that you're still exponentiating when you put in that division part. So example 5 gives us a problem, college campus, 5,000 students, one student returns from vacation with a contagious flu virus. The spread is modeled by, and in example 5, I want you to look at this logistics growth function, And I want you to turn back and look at logistics growth model on page 221. And you're going to see a shape similar to this, where things are increasing rapidly, and then we see that they start to decrease. So we can understand that that would possibly fit something like the spread of the flu, where after everybody's contagious, there's no more spread, or the population in a confined area of certain organism that's eating up all the food. We know that at a certain point, from here to the middle, in this region, things are growing rapidly, but then start to, in this region, start to die back or not spread as quickly. So after reading example 5, I'd like you to try problem 43 and come right back here, and we'll look at that solution. So 43 is logistics growth. We have 100 endangered animals, species in a game preserve. Organization believes the preserve has a carrying capacity of 1,000, and that the growth of the herd will follow this logistic curve that we've written up here. What's the population after 5 months? Well, if we look at the function, we know and understand that typically T stands for time. So we're going to go to that part of our function and input the first part, which says, what's the population after 5 months? So we're going to take this model and input the value 5. Then we see that we have no more variables. Inputting that value for problem 43 would give us roughly 200. So P of 5 would give us roughly 203 animals if you calculate it correctly. Part B says, when will the population be? So we have two variables here. We have months and we have population. So when will the population be 500? So we're going to input that value. 500 is equal to 1,000 divided by 1 plus 9 times e to the negative 0.1656t. Now we understand we're trying to solve for that value t. So what we're going to do is this. Could we divide both sides by 500 and multiply both sides by this in one step? So dividing both sides by 500, 1,000 divided by 500 on the right hand side would yield 2, and we canceled that out. Multiplying both sides by 1 plus 9 e to the negative 0.1656t, and just simple algebraic steps. Subtracting 1, we get 9e to the negative 0.1656t is equal to 1. Of course, we're going to divide both sides by 9. This is for Joran. He loves algebra. Why do I have to do all this algebra? Well, I explained to him calculus is 9/10 algebra. If you're not into fractions, it's 0.9 or 90%. Whatever you prefer. How many months will the population reach 500? We're still solving. We're going to take the natural log of both sides, yielding negative 0.1656t, and the natural log of 1/9. So we're going to have the log of 1 divided by 9 all over negative 0.1656, leaving us with t. If you were able to follow those steps and solving this equation would give us 13 months.